Chapter 15. Transition to jet-powered airplanes. Introduction. This chapter contains an overview of jet-powered airplane operations. The information contained in this chapter is meant to be a useful preparation for, and a supplement to, formal and structured jet airplane qualification training. The intent of this chapter is to provide information on the major differences a pilot will encounter when transitioning to jet-powered airplanes. In order to achieve this in a logical manner, the major differences between jet-powered airplanes and piston-powered airplanes have been approached by addressing two distinct areas: differences in technology, or how the airplane itself differs, and differences in pilot technique, or how the pilot addresses the technological differences through the application of different techniques. For airplane-specific information, a pilot should refer to the FAA-approved airplane flight manual for that airplane. 15:1. Jet engine basics. A jet engine is a gas turbine engine. A jet engine develops thrust by accelerating a relatively small mass of air to very high velocity, as opposed to a propeller, which develops thrust by accelerating a much larger mass of air to a much slower velocity. Piston and gas turbine engines are internal combustion engines and have a similar basic cycle of operation, that is, induction, compression, combustion, expansion, and exhaust. Air is taken in and compressed, and fuel is injected and burned. The hot gases then expand and supply a surplus of power over that required for compression and are finally exhausted. In both piston and jet engines, the efficiency of the cycle is improved by increasing the volume of air taken in and the compression ratio. Part of the expansion of the burned gases takes place in the turbine section of the jet engine, providing the necessary power to drive the compressor, while the remainder of the expansion takes place in the nozzle of the tailpipe in order to accelerate the gas to a high-velocity jet, thereby producing thrust. Figure 15:1. In theory, the jet engine is simpler and more directly converts thermal energy, the burning and expansion of gases, into mechanical energy, thrust. The piston or reciprocating engine, with all of its moving parts, must convert the thermal energy into mechanical energy and then finally into thrust by rotating a propeller. One of the advantages of the jet engine over the piston engine is the jet engine's capability of producing much greater amounts of thrust horsepower at the high altitudes and high speeds. In fact, turbojet engine efficiency increases with altitude and speed. Although the propeller-driven airplane is not nearly as efficient as the jet, particularly at the higher altitudes and cruising speeds required in modern aviation, one of the few advantages the propeller-driven airplane has over the jet is that maximum thrust is available almost at the start of the takeoff roll. Initial thrust output of the jet engine on takeoff is relatively lower and does not reach peak efficiency until the higher speeds. The fanjet or turbofan engine was developed to help compensate for this problem and is, in effect, a compromise between the pure jet engine, turbojet, and the propeller engine. Like other gas turbine engines, the heart of the turbofan engine is the gas generator, the part of the engine that produces the hot, high-velocity gases. Similar to turboprops, turbofans have a low-pressure turbine section that uses most of the energy produced by the gas generator. The low-pressure turbine is mounted on a concentric shaft that passes through the hollow shaft of the gas generator, connecting it to a ducted fan at the front of the engine. Figure 15:2. Air enters the engine, passes through the fan, and splits into two separate paths. Some of it flows around, bypasses the engine core, hence its name, bypass air. The air drawn into the engine for the gas generator is the core airflow. The amount of air that bypasses the core compared to the amount drawn into the gas generator determines a turbofan's bypass ratio. Turbofans efficiently convert fuel into thrust because they produce low-pressure energy spread over a large fan disk area. While a turbojet engine uses the entire gas generator's output to produce thrust in the form of a high-velocity exhaust gas jet, cool, low-velocity bypass air produces between 30% and 70% of the thrust produced by a turbofan engine. The fan jet concept increases the total thrust of the jet engine, particularly at the lower speeds and altitudes. Although efficiency at the higher altitudes is lost, turbofan engines are subject to a large lapse in thrust with increasing altitude. The direction of flight. Concentric shaft. Ducted fan. Gas generator. Low-pressure turbine. Figure 15:1. Basic turbojet engine. 15:2. Combustion. Combustion. Exhaust. Temperature limits, even for a very few seconds, may result in serious heat damage to turbine blades and other components. Depending on the make and model, Gas temperatures can be measured at a number of different locations within the engine. The associated engine gauges therefore have different names according to their location. For instance, exhaust gas temperature, EGT, the temperature of the exhaust gases as they enter the tailpipe after passing through the turbine. Fan air. Fan air. Inlet air. Figure 15.2. Turbofan engine. Turbofan engine increases acceleration, decreases the takeoff roll, improves initial climb performance, and often has the effect of decreasing specific fuel consumption. Specific fuel consumption is a ratio of the fuel used by an engine and the amount of thrust it produces. Operating the jet engine in a jet engine, thrust is determined by the amount of fuel injected into the combustion chamber. The power controls on most turbojet and turbofan-powered airplanes consist of just one thrust lever for each engine, because most engine control functions are automatic. The thrust lever is linked to a fuel control and/or electronic engine computer that meters fuel flow based upon revolutions per minute, RPM, internal temperatures, ambient conditions, and other factors. Figure 15.3. In a jet engine, each major rotating section usually has a separate gauge devoted to monitoring its speed of rotation. Depending on the make and model, a jet engine may have an N1 gauge that monitors the low-pressure compressor section and/or fan speed in turbofan engines. The gas generator section may be monitored by an N2 gauge, while triple-spool engines may have an N3 gauge as well. Each engine section rotates at many thousands of RPM. Their gauges therefore are calibrated in % of RPM rather than actual RPM, for ease of display and interpretation. Figure 15.4. The temperature of turbine gases must be closely monitored by the pilot. As in any gas turbine engine, exceeding. Figure 15.3. Jet engine power controls. 15-3. TAT plus 13C. Dash. 1028.808. 2. 6. 4. 10.8. 6. 4. N1. 2. 65. 768. EGT. 0.42. FF. 3.50. 2. 3. 33.1. 427.306.912.15.1. 8. 2. 1. Start valve. ENG1 open. ENG2. 94.80. 66.8. 94.5. 1. 2. 5. Nose gear. Left gear. Right gear. Center 11 260 fuel EG. 1 2350. 2 2350. N2. FF. 3.50. 0.40. Oil. Press. 25. 64. 15. 17. Oil temp. Oil QTY. 32. 17. 2.5. Fib. 1.8. 10. 15. 25. L. Up. Flaps. 30. 40. The flaps transit. The flaps. Exit. Speed brake. Ahead. Speed brakes. Extended. Figure 15.4. Jet engine RPM gauges. Turbine inlet temperature, TIT, the temperature of the gases from the combustion section of the engine as they enter the first stage of the turbine. The TIT is the highest temperature inside a gas turbine engine and is one of the limiting factors of the amount of power the engine can produce. TIT, however, is difficult to measure. Therefore, EGT, which relates to TIT, is normally the parameter measured. Interstage turbine temperature, ITT, the temperature of the gases between the high-pressure and low-pressure turbine wheels. Turbine outlet temperature, TOT, like EGT, turbine outlet temperature is taken aft of the turbine wheels. Jet engine ignition. Most jet engine ignition systems consist of two igniter plugs, which are used during the ground or air starting of the engine. Once the start is completed, this ignition either automatically goes off or is turned off, and from this point on, the combustion in the engine is a continuous process. Continuous ignition. An engine is sensitive to the flow characteristics of the air that enters the intake of the engine nacelle. So long as the flow of air is substantially normal, the engine continues to run smoothly. However, particularly with rear-mounted engines that are sometimes in a position to be affected by disturbed airflow from the wings, there are some abnormal flight situations that could cause a compressor stall or flame out of the engine. These abnormal flight conditions would usually be associated with abrupt pitch changes such as might be encountered in severe turbulence or a stall. 15-4. In order to avoid the possibility of engine flameout from the above conditions, or from other conditions that might cause ingestion problems, such as heavy rain, ice, or possible bird strike, most jet engines are equipped with a continuous ignition system. This system can be turned on and used continuously whenever the need arises. In many jets, as an added precaution, this system is normally used during takeoffs and landings. Many jets are also equipped with an automatic ignition system that operates both igniters whenever the airplane stall warning or stick shaker is activated. Fuel heaters. Because of the high altitudes and extremely cold outside air temperatures in which the jet flies, it is possible to supercool the jet fuel to the point that the small particles of water suspended in the fuel can turn to ice crystals and clog the fuel filters leading to the engine. For this reason, jet engines are normally equipped with fuel heaters. The fuel heater may be of the automatic type that constantly maintains the fuel temperature above freezing, or they may be manually controlled by the pilot. Setting power. On some jet airplanes, thrust is indicated by an engine pressure ratio, EPR, gauge. EPR can be thought of as being equivalent to the manifold pressure on the piston engine. EPR is the difference between turbine discharge pressure and engine inlet pressure. It is an indication of what the engine has done with the raw air scooped in. For instance, an EPR setting of 2.24 means that the discharge pressure relative to the inlet pressure is 2.24 to 1. On these airplanes, the EPR gauge is the primary reference used to establish power settings. Figure 15.5. TAT 13 degrees Celsius. 2.00. 2.00. 2.00. 2.00. EPR. 25.8. 25.8. 25.8. 25.8. N1. Cab. Light off fuel valve 1 op fuel valve 2 op fuel valve 3 op fuel valve 4 op elect gen 1 on elect gen 2 on elect gen 3 on elect gen 4 on Hyder sys 1 Hyder sys 2 Hyder sys 3 Hyder sys 4. 339. 339. 339. 339. EGT. Trim 0.0. Total fuel 335.0 pounds times 1000. Figure 15.5. EPR gauge. Fan speed, N1, is the primary indication of thrust on most turbofan engines. Fuel flow provides a secondary thrust indication, and cross-checking for proper fuel flow can help in spotting a faulty N1 gauge. Turbofans also have a gas generator turbine tachometer, N2. They are used mainly for engine starting and some system functions. In setting power, it is usually the primary power reference, EPR or N1, that is most critical and is the gauge that first limits the forward movement of the thrust levers. However, there are occasions where the limits of either RPM or temperature can be exceeded. The rule is, movement of the thrust levers must be stopped and power set at whichever the limits of EPR, RPM, or temperature is reached first. Thrust-to-thrust lever relationship in a piston engine, propeller-driven airplane, thrust is proportional to RPM, manifold pressure, and propeller blade angle, with manifold pressure being the most dominant factor. At a constant RPM, thrust is proportional to throttle lever position. In a jet engine, however, thrust is quite disproportional to thrust lever position. This is an important difference that the pilot transitioning into jet-powered airplanes must become accustomed to. On a jet engine, thrust is proportional to RPM, mass flow, and temperature, fuel/air ratio. These are matched, and a further variation of thrust results from the compressor efficiency at varying RPM. The jet engine is most efficient at high RPM, where the engine is designed to be operated most of the time. As RPM increases, mass flow, temperature, and efficiency also increase. Therefore, much more thrust is produced per increment of throttle movement near the top of the range than near the bottom. One thing that seems different to the piston pilot transitioning into jet-powered airplanes is the rather large amount of thrust lever movement between the flight idle position and full power as compared to the small amount of movement of the throttle in the piston engine. For instance, an inch of throttle movement on a piston may be worth 400 horsepower wherever the throttle may be. On a jet, an inch of thrust lever movement at a low RPM may be worth only 200 pounds of thrust, but at a high RPM that same inch of movement might amount to closer to 2,000 pounds of thrust. Because of this, in a situation where significantly more thrust is needed and the jet engine is at low RPM, it does not do much good to merely inch the thrust lever forward. Substantial thrust lever movement is in order. This is not to say that rough or abrupt thrust lever action is standard operating procedure. If the power setting is already high, it may take only a small amount of movement. However, there are two characteristics of the jet engine that work against the normal habits of the piston engine pilot. One is the variation of thrust with RPM, and the other is the relatively slow acceleration of the jet engine. Variation of thrust with RPM. Whereas piston engines normally operate in the range of 40% to 70% of available RPM, jets operate most efficiently in the 85% to 100% range, with a flight idle RPM of 50% to 60%. The range from 90% to 100% in jets may produce as much thrust as the total available at 70%. Figure 15.6. TSURH. T. MUMXAM. I. T. NECREP. 100. 90. 80. 70. 60. 50. 40. 30. 20. 10. 0. Variation of thrust with RPM, constant altitude and velocity. 0. 10. 20. 30. 40. 50. 60. 70. 80 90 100. % maximum RPM. Figure 15.6. Variation of thrust with RPM. 15 to 5. Slow acceleration of the jet engine in a propeller-driven airplane. The constant speed propeller keeps the engine turning at a constant RPM within the governing range, and power is changed by varying the manifold pressure. Acceleration of the piston from idle to full power is relatively rapid, somewhere on the order of 3 to 4 seconds. The acceleration on the different jet engines can vary considerably, but it is usually much slower. Efficiency in a jet engine is highest at high RPM, where the compressor is working closest to its optimum conditions. At low RPM, the operating cycle is generally inefficient. If the engine is operating at normal approach RPM and there is a sudden requirement for increased thrust, the jet engine responds immediately and full thrust can be achieved in about 2 seconds. However, at a low RPM, sudden full power application tends to overfuel the engine, resulting in possible compressor surge, excessive turbine temperatures, compressor stall and/or flameout. To prevent this, various limiters, such as compressor bleed valves, are contained in the system and serve to restrict the engine until it is at an RPM at which it can respond to a rapid acceleration demand without distress. This critical RPM is most noticeable when the engine is at idle RPM, and the thrust lever is rapidly advanced to a high power position. Engine acceleration is initially very slow, but can change to very fast after about 78% RPM is reached. Figure 15.7. Even though engine acceleration is nearly instantaneous after about 78% RPM, total time to accelerate from idle RPM to full power may take as much as 8 seconds. For this reason, most jets are operated at a relatively high RPM. 8. 6. 4. 2. 78%. CES. TSURHT. LL. I. UF. EBEHCA. OT. EMT. I. 60%. 100%. RPM. Figure 15.7. Typical jet engine acceleration times. 15 to 6. During the final approach to landing or at any other time that immediate power may be needed. Jet engine efficiency. Maximum operating altitudes for general aviation turbojet airplanes now reach 51,000 feet. The efficiency of the jet engine at high altitudes is the primary reason for operating in the high-altitude environment. The specific fuel consumption of jet engines decreases as the outside air temperature decreases for constant engine RPM and true airspeed, TAS. Thus, by flying at a high altitude, the pilot is able to operate at flight levels where fuel economy is best and with the most advantageous cruise speed. For efficiency, jet airplanes are typically operated at high altitudes where cruise is usually very close to RPM or EGT limits. At high altitudes, little excess thrust may be available for maneuvering. Therefore, it is often impossible for the jet airplane to climb and turn simultaneously, and all maneuvering must be accomplished within the limits of available thrust and without sacrificing stability and controllability. Absence of propeller effect. The absence of a propeller has a significant effect on the operation of jet-powered airplanes that the transitioning pilot must become accustomed to. The effect is due to the absence of lift from the propeller slipstream and the absence of propeller drag. Absence of propeller slipstream. A propeller produces thrust by accelerating a large mass of air rearwards, and, especially with wing-mounted engines, this air passes over a comparatively large percentage of the wing area. On a propeller-driven airplane, the lift that the wing develops is the sum of the lift generated by the wing area not in the wake of the propeller, as a result of airplane speed, and the lift generated by the wing area influenced by the propeller slipstream. By increasing or decreasing the speed of the slipstream air, it is possible to increase or decrease the total lift on the wing without changing airspeed. For example, a propeller-driven airplane that is allowed to become too low and too slow on an approach is very responsive to a quick blast of power to salvage the situation. In addition to increasing lift at a constant airspeed, stalling speed is reduced with power on. A jet engine, on the other hand, also produces thrust by accelerating a mass of air rearward, but this air does not pass over the wings. Therefore, there is no lift bonus at increased power at constant airspeed and no significant lowering of power on stall speed. In not having propellers, the jet-powered airplane is -2 assets. It is not possible to produce increased lift instantly by simply increasing power. It is not possible to lower stall speed by simply increasing power. The 10-knot margin, roughly the difference between power off and power on stall speed on a propeller-driven airplane for a given configuration, is lost. Add the poor acceleration response of the jet engine, and it becomes apparent that there are 3 ways in which the jet pilot is worse off than the propeller pilot. For these reasons, there is a marked difference between the approach qualities of a piston engine airplane and a jet. In a piston engine airplane, there is some room for error. Speed is not too critical and a burst of power salvages an increasing sink rate. In a jet, however, there is little room for error. If an increasing sink rate develops in a jet, the pilot must remember 2 points in the proper sequence. 1. Increased lift can be gained only by accelerating airflow over the wings, and this can be accomplished only by accelerating the entire airplane. 2. The airplane can be accelerated, assuming altitude loss cannot be afforded, only by a rapid increase in thrust, and here, the slow acceleration of the jet engine, possibly up to 8 seconds, becomes a factor. Salvaging an increasing sink rate on an approach in a jet can be a very difficult maneuver. The lack of ability to produce instant lift in the jet, along with the slow acceleration of the engine, necessitates a stabilized approach to a landing where full landing configuration, constant airspeed, controlled rate of descent, and relatively high power settings are maintained until over the threshold of the runway. This allows for almost immediate response from the engine in making minor changes in the approach speed or rate of descent and makes it possible to initiate an immediate go-around or missed approach if necessary. Absence of propeller drag. When the throttles are closed on a piston-powered airplane, the propellers create a vast amount of drag, and airspeed is immediately decreased or altitude lost. The effect of reducing power to idle on the jet engine, however, produces no such drag effect. In fact, at an idle power setting, the jet engine still produces forward thrust. The main advantage is that the jet pilot is no longer faced with a potential drag penalty of a runaway propeller or a reversed propeller. A disadvantage, however, is the freewheeling effect forward thrust at idle has on the jet. While this occasionally can be used to advantage, such as in a long descent, it is a handicap when it is necessary to lose speed quickly, such as when entering a terminal area or when in a landing flare. The lack of propeller drag, along with the aerodynamically clean airframe of the jet, are new to most pilots, and slowing the airplane down is one of the initial problems encountered by pilots transitioning into jets. Speed margins. The typical piston-powered airplane had to deal with 2 maximum operating speeds. VNO maximum structural cruising speed, represented on the airspeed indicator by the upper limit of the green arc. It is, however, permissible to exceed VNO and operate in the caution range, yellow arc, in certain flight conditions. VNE never exceeds speed, represented by a red line on the airspeed indicator. These speed margins in the piston airplanes were never of much concern during normal operations because the high drag factors and relatively low cruise power settings kept speeds well below these maximum limits. Maximum speeds in jet airplanes are expressed differently and always define the maximum operating speed of the airplane, which is comparable to the VNE of the piston airplane. These maximum speeds in a jet airplane are referred to as VMO, maximum operating speed expressed in terms of knots. MMO, maximum operating speed expressed in terms of a decimal of Mach speed, speed of sound. To observe both limits VMO and MMO, the pilot of a jet airplane needs both an airspeed indicator and a Mach meter, each with appropriate red lines. In some general aviation jet airplanes, these are combined into a single instrument that contains a pair of concentric indicators, one for the indicated airspeed and the other for indicated Mach number. Each is provided with an appropriate red line. Figure 15.8. It looks much like a conventional airspeed indicator but has a barber pole that automatically moves so as to display the applicable speed limit at all times. Because of the higher available thrust and very low drag design, the jet airplane can very easily exceed its speed margin even in cruising flight and, in fact, in some airplanes in a shallow climb. The handling qualities in a jet can change drastically when the maximum operating speeds are exceeded. 15-7. Power airspeed indicator. Nav 1 108.00 117.95 117.95 Nav 2 108.00 Dis. Underscore dot underscore NM. BRG underscore degree. 136.975 136.975 118.000 118.000 Com 1 Com 2 240 230 Nav 221 210 9 200 190 MO and MMO barber pole 10 Traffic 240 230 221 210 9 200 190 180 M.579 North up 10 5 5 5 5 HDG 360 degrees 360 degrees CRS 360 degrees GPS ENR underscore 31,300 31,200 31,120 31,000 80 30,900 30,800 30,700 4 2 2 4 Borrow 180 M.579 TA off scale rag 10 degrees Celsius ESA minus 0 degrees Celsius TRFC/map 2 nautical miles Mach airspeed Sensor ADF/DME/TFC MSG XPDR 1200 volt LCL 1819 and 9 seconds Figure 15.8 Jet airspeed indicator. High-speed airplanes designed for subsonic flight are limited to some Mach number below the speed of sound to avoid the formation of shock waves that begin to develop as the airplane nears Mach 1.0. These shock waves, and the adverse effects associated with them, can occur when the airplane speed is substantially below Mach 1.0. The Mach speed at which some portion of the airflow over the wing first equals Mach 1.0 is termed the critical Mach number, MCR. This is also the speed at which a shock wave first appears on the airplane. There is no particular problem associated with the acceleration of the airflow up to Mach crit, the point where Mach 1.0 is encountered. However, a shock wave is formed at the point where the airflow suddenly returns to subsonic flow. This shock wave becomes more severe and moves aft on the wing as speed of the wing is increased and eventually flow separation occurs behind the well-developed shock wave. Figure 15.9. If allowed to progress well beyond the MMO for the airplane, this separation of air behind the shock wave can result in severe buffeting and possible loss of control or upset. Because of the changing center of lift of the wing resulting from the movement of the shock wave, the pilot experiences pitch change tendencies as the airplane moves through the transonic speeds up to and exceeding MMO. Figure 15.10. 15-8. As the graph in Figure 15.10 illustrates, initially as speed is increased up to Mach 0.72, The wing develops an increasing amount of lift, requiring a nose-down force or trim to maintain level flight. With increased speed and the aft movement of the shock wave, the wing's center of pressure also moves aft, causing the start of a nose-down tendency or tuck. By Mach 0.9, the nose-down forces are well developed to a point where a total of 70 pounds of back pressure are required to. Maximum local velocity is less than sonic. Normal shock wave. Subsonic. Possible separation. Normal shock. M equals 0.72, critical Mach number, ONIC sub ERS flow W. M equals 0.77. ONIC W. Sub ERS flow. M equals 0.82. Separation. Normal shock. Figure 15.9. Transonic flow patterns. SDNUOP. NI. ECROF. KCIT. S. 70. 60. 50. 40. 30. 20. 10. 0. 10. 20. 0. Pull. Push. 0.3. 0.4. 0.5. 0.6. 0.7. 0.8. 0.9. Mach number. Figure 15.10. Example of stick forces versus Mach number in a typical jet airplane. Hold the nose up. If allowed to progress unchecked, Mach tuck may eventually occur. Although Mach tuck develops gradually, if it is allowed to progress significantly, the center of pressure can move so far rearward that there is no longer enough elevator authority available to counteract it, and the airplane could enter a steep, sometimes unrecoverable, dive. An alert pilot would have observed the high airspeed indications, experienced the onset of buffeting, and responded to oral warning devices long before encountering the extreme stick forces shown. However, in the event that corrective action is not taken and the nose is allowed to drop, increasing airspeed even further, the situation could rapidly become dangerous. As the Mach speed increases beyond the airplane's MMO, the effects of flow separation and turbulence behind the shock wave become more severe. Eventually, the most powerful forces causing Mach tuck are a result of the buffeting and lack of effective downwash on the horizontal stabilizer because of the disturbed airflow over the wing. This is the primary reason for the development of the T-tail configuration on some jet airplanes, which places the horizontal stabilizer as far as practical from the turbulence of the wings. Also, because of the critical aspects of high-altitude/high Mach flight, most jet airplanes capable of operating in the Mach speed ranges are designed with some form of trim and autopilot Mach compensating device, stick puller, to alert the pilot to inadvertent excursions beyond its certificated MMO. Recovery from overspeed conditions. A pilot must be aware of all the conditions that could lead to exceeding the airplane's maximum operating speeds. Good attitude, instrument flying skills, and good power control are essential. The pilot should be aware of the symptoms that will be experienced in the particular airplane as the VMO or MMO is being approached. These may include nose-down tendency and need for back pressure or trim. Mild buffeting as airflow separation begins to occur. After critical Mach speed. Activation of an overspeed warning or high speed. Envelope protection. The pilot's response to an overspeed condition should be to immediately slow the airplane by reducing the power to flight idle. It will also help to smoothly and easily raise the pitch attitude to help dissipate speed. The use of speed brakes can also aid in slowing the airplane. If, however, the nose-down stick forces have progressed to the extent that they are excessive, some speed brakes will tend to further aggravate the nose-down tendency. Under most conditions, this additional pitch-down force is easily controllable, and since speed brakes can normally be used at any speed, they are a very real asset. If the first two options are not successful in slowing the airplane, a last resort option would be to extend the landing gear, if possible. This creates enormous drag and possibly some nose-up pitch. This would be considered an emergency maneuver. The pilot transitioning into jet airplanes must be familiar with the manufacturer's recommended procedures for dealing with overspeed conditions contained in the FAA-approved airplane flight manual for the particular make and model airplane. Mach buffet boundaries. Thus far, only the Mach buffet that results from excessive speed has been addressed. The transitioning pilot, however, should be aware that Mach buffet is a function of the speed of the airflow over the wing, not necessarily the airspeed of the airplane. Anytime that too great a lift demand is made on the wing, whether from too fast an airspeed or from too high an angle of attack, AOA, near the MMO, the high-speed buffet will occur. However, there are also occasions when the buffet can be experienced at much slower speeds known as low-speed Mach buffet. The most likely situations that could cause the low-speed buffet would be when an airplane is flown at too slow of a speed for its weight and altitude, causing a high OA. This very high OA would have the same effect of increasing airflow over the upper surface of the wing to the point that all of the same effects of the shock waves in buffet would occur as in the high-speed buffet situation. 15-9. The OA of the wing has the greatest effect on inducing the Mach buffet, or pre-stall buffet, at either the high or low speed boundaries for the airplane. The conditions that increase the OA, hence the speed of the airflow over the wing and chances of Mach buffet are: high altitudes. The higher the airplane flies, the thinner the air and the greater the OA required to produce the lift needed to maintain level flight. Heavy weights. The heavier the airplane, the greater the lift required of the wing, and all other things being equal, the greater the OA. G-loading. An increase in the G-loading of the wing results in the same situation as increasing the weight of the airplane. It makes no difference whether the increase in G-forces is caused by a turn, rough control usage, or turbulence. The effect of increasing the wing's OA is the same. An airplane's indicated airspeed decreases in relation to true airspeed as altitude increases. As the indicated airspeed decreases with altitude, it progressively merges with the low-speed buffet boundary where pre-stall buffet occurs for the airplane at a load factor of 1.0 g. The point where the high-speed Mach indicated airspeed and low-speed buffet boundary indicated airspeed merge is the airplane's absolute or aerodynamic ceiling. This is where if an airplane flew any slower it would exceed its stalling OA and experience low-speed buffet. Additionally, if it flew any faster it would exceed MMO, potentially leading to high-speed buffet. This critical area of the airplane's flight envelope is known as coffin corner. All airplanes are equipped with some form of stall warning system. Crews must be aware of systems installed on their airplanes, stick pushers, stick shakers, audio alarms, etc., and their intended function. In a high-altitude environment, airplane buffet is sometimes the initial indicator of problems. Mach buffet occurs as a result of supersonic airflow on the wing. Stall buffet occurs at angles of attack that produce airflow disturbances, burbling, over the upper surface of the wing which decreases lift. As density altitude increases, the OA that is required to produce an airflow disturbance over the top of the wing is reduced until the density altitude is reached where Mach buffet and stall buffet converge, coffin corner. When this phenomenon is encountered, serious consequences may result causing loss of airplane control. Increasing either gross weight or load factor, G factor, will increase the low-speed buffet and decrease Mach buffet speeds. A typical jet airplane flying at 51,000 feet altitude at 1.0 g may encounter Mach buffet slightly above the airplane's MMO, 0.82 Mach, and low-speed buffet at 0.60. 15-10 Mach. However, only 1.4 g, an increase of only 0.4 g, may bring on buffet at the optimum speed of 0.73 Mach, and any change in airspeed, bank angle, or gust loading may reduce this straight and level flight 1.4 g protection to no protection at all. Consequently, a maximum cruising flight altitude must be selected which will allow sufficient buffet margin for necessary maneuvering and for gust conditions likely to be encountered. Therefore, it is important for pilots to be familiar with the use of charts showing cruise maneuver and buffet limits. Figure 1511. The transitioning pilot must bear in mind that the maneuverability of the jet airplane is particularly critical, especially at the high altitudes. Some jet airplanes have a narrow span between the high and low speed buffets. One airspeed that the pilot should have firmly fixed in memory is the manufacturer's recommended gust penetration speed for the particular make and model airplane. This speed is normally the speed that would give the greatest margin between the high and low speed buffets, and may be considerably higher than design maneuvering speed, VA. This means that, unlike piston airplanes, there are times when a jet airplane should be flown in excess of VA during encounters with turbulence. Pilots operating airplanes at high speeds must be adequately trained to operate them safely. This training cannot be complete until pilots are thoroughly educated in the critical aspects of the aerodynamic factors pertinent to Mach flight at high altitudes. Low-speed flight. The jet airplane wing, designed primarily for high-speed flight, has relatively poor low-speed characteristics. As opposed to the normal piston-powered airplane, The jet wing has less area relative to the airplane's weight, a lower aspect ratio, long chord/short span, and thin airfoil shape, all of which amount to the need for speed to generate enough lift. The swept wing is additionally penalized at low speeds because its effective lift is proportional to airflow speed that is perpendicular to the leading edge. This airflow speed is always less than the airspeed of the airplane itself. In other words, the airflow on the swept wing has the effect of persuading the wing into believing that it is flying slower than it actually is. The first real consequence of poor lift at low speeds is a high stall speed. The second consequence of poor lift at low speeds is the manner in which lift and drag vary at those low speeds. As a jet airplane is slowed toward its minimum drag speed, VMD or L/Dmax, total drag increases at a much greater rate than the changes in lift, resulting in a sinking flight path. If the pilot attempts to increase lift by increasing the OA, airspeed will be further reduced, resulting in a further increase. 19,000 pounds, 19,000 pounds, 18,000 pounds, 18,000 pounds, 17,000 pounds, 17,000 pounds, 16,000 pounds, 16,000 pounds, 15,000 pounds, 15,000 pounds, 14,000 pounds, 14,000 pounds, 13,000 pounds, 13,000 pounds, 12,000 pounds, 12,000 pounds, 11,000 pounds, 11,000 pounds. C. LV0E0AL5,0 ES. 10,000. 15,000. 20,000. Pressure altitude minus 25,000 feet. 30,0005, 0. 0. 3. 0. MMO. B. 4. 0. 0 0, 045, 0 0 0. 1. D2. 3. 0.1. 0.2. 0.3. 0.4. 0.5. 0.6. Load factor G. Indicated Mach number. A 0.7. 0.8. Figure 1511. Mach buffet boundary chart. In drag and sink rate as the airplane slides up the backside of the power required curve. The sink rate can be arrested in one of two ways. Fact that drag increases more rapidly than lift, causing a sinking flight path, is one of the most important aspects of jet airplane flying qualities. Pitch attitude can be substantially reduced to reduce the OA and allow the airplane to accelerate to a speed above VMD, where steady flight conditions can be re-established. This procedure, however, will invariably result in a substantial loss of altitude. Thrust can be increased to accelerate the airplane to a speed above VMD to re-establish steady flight conditions. The amount of thrust must be sufficient to accelerate the airplane and regain altitude lost. Also, if the airplane has slid a long way up the backside of the power required drag curve, drag will be very high and a very large amount of thrust will be required. In a typical piston engine airplane, VMD in the clean configuration is normally at a speed of about 1.3 versus figure 1512. Flight below VMD on a piston engine airplane is well identified and predictable. In contrast, in a jet airplane flight in the area of VMD, typically 1.5 to 1.6 versus, does not normally produce any noticeable changes in flying qualities other than a lack of speed stability, a condition where a decrease in speed leads to an increase in drag which leads to a further decrease in speed and hence a speed divergence. A pilot who is not cognizant of a developing speed divergence may find a serious sink rate developing at a constant power setting, and a pitch attitude that appears to be normal. The stalling characteristics of the swept-wing jet airplane can vary considerably from those of the normal straight-wing airplane. The greatest difference that will be noticeable to the pilot is the lift developed versus angle of attack. An increase in angle of attack of the straight wing produces a substantial and constantly increasing lift vector up to its maximum coefficient of lift, and soon thereafter flow separation, stall, occurs with a rapid deterioration of lift. By contrast, the swept wing produces a much more gradual buildup of lift with a less well-defined maximum coefficient. This less defined peak also means that a swept wing may not have as dramatic loss of lift at angles of attack beyond its maximum lift coefficient. However, these high lift conditions are accompanied by high drag, which results in a high rate of descent. Figure 1513. The differences in the stall characteristics between a conventional straight wing/low tailplane, non-T-tail, airplane and a swept-wing T-tail airplane center around two main areas. The basic pitching tendency of the airplane at the stall. Tail effectiveness and stall recovery. 15 to 11. A. DERIUQER. TSURHT. 4000. 3000. 2000. 1000. 0. 0. Jet aircraft. Total drag. Minimum drag. Or L/Dmax. Parasite drag. Induced drag. 100. 200. 300. 400. 500. B. DERIUQER. REWOB. 4000. 3000. 2000. 1000. 0. 0. Propeller-driven aircraft. Total power required. Minimum power required. L/Dmax. Parasite power required. Power required. 100. 200. 300. 400. 500. Airspeed. Airspeed. Figure 1512. Thrust and power required curves, jet aircraft versus propeller-driven aircraft. On a conventional straight-wing/low tailplane airplane, the weight of the airplane acts downwards forward of the lift acting upwards, producing a need for a balancing force acting downwards from the tailplane. As speed is reduced by gentle up-elevator deflection, the static stability of the airplane causes a nose-down tendency. This is countered by further up-elevator to keep the nose coming up and the speed decreasing. As the pitch attitude increases, the low-set tail is immersed in the wing wake, which is slightly turbulent, low-energy air. The accompanying aerodynamic buffeting serves as a warning of impending stall. The reduced effectiveness of the tail prevents the pilot from forcing the airplane into a deeper stall. Figure 1514. The conventional straight-wing airplane conforms to the familiar nose-down pitching tendency at the stall and gives the entire airplane a fairly pronounced nose-down pitch. At the moment of stall, the wing wake passes more or less straight rearward and passes above the tail. The tail is now immersed in high-energy air where it experiences a sharp increase in positive OA causing upward lift. This lift then assists the nose-down pitch in decreasing wing OA essential to stall recovery. In a swept-wing jet with a T-tail and rear fuselage-mounted engines, the two qualities that are different from its straight-wing low tailplane counterpart are the pitching tendency. T. I. NECIFF. EOC. TFI. L. Straight-wing EPTW and G. W. S. Angle of attack. Figure 15 to 13. Stall versus angle of attack, swept wing versus straight wing. Figure 1514. Stall progression, typical straight-wing airplane. 15 to 12. Of the airplane as the stall develops and the loss of tail effectiveness at the stall. The handling qualities down to the stall are much the same as the straight-wing airplane except that the high T-tail remains clear of the wing wake and provides little or no warning in the form of a pre-stall buffet. Also, the tail is fully effective during the speed reduction towards the stall, and remains effective even after the wing has begun to stall. This enables the pilot to drive the wing into a deeper stall at a much greater OA. At the stall, two distinct things happen. After the stall, the swept-wing T-tail airplane tends to pitch up rather than down, and the T-tail can become immersed in the wing wake, which is low-energy turbulent air. This greatly reduces tail effectiveness and the airplane's ability to counter the nose-up pitch. Also, if the OA increases further, the disturbed, relatively slow air behind the wing may sweep across the tail at such a large angle that the tail itself stalls. If this occurs, the pilot loses all pitch control and will be unable to lower the nose. The pitch up just after the stall is worsened by large reduction in lift and a large increase in drag, which causes a rapidly increasing descent path, thus compounding the rate of increase of the wing's OA. Figure 1515. A slight pitch-up tendency after the stall is a characteristic of the swept or tapered wings. With these types of wings, there is a tendency for the wing to develop a spanwise airflow towards the wingtip when the wing is at high angles of attack. This leads to a tendency for separation of airflow, and the subsequent stall, to occur at the wingtips first. Figure 1516. Pre-stall. Stalled. Figure 1515. Stall progression, swept wing airplane. In an unmodified swept wing, the tip's first stall results in a shift of the center of lift of the wing in a forward direction relative to the center of gravity of the airplane, causing a tendency for the nose to pitch up. A disadvantage of a tip-first stall is that it can involve the ailerons and aero roll control. To satisfy certification criteria, airplane manufacturers may have to tailor the airfoil characteristics of a wing as it proceeds from the root to the tip so that a pilot can still maintain wings level flight with normal use of the controls. Still, more aileron will be required near stall to correct roll excursion than in normal flight, as the effectiveness of the ailerons will be reduced and feel mushy. This change in feel can be an important recognition cue that the airplane may be stalled. As previously stated, when flying at a speed near VMD, an increase in NOAA causes drag to increase faster than lift and the airplane begins to sink. It is essential to understand that this increasing sinking tendency, at a constant pitch attitude, results in a rapid increase in NOAA as the flight path becomes deflected downwards. Figure 15 to 17. Furthermore, once the stall has developed and a large amount of lift has been lost, the airplane will begin to sink rapidly, and this will be accompanied by a corresponding rapid increase in NOAA. This is the beginning of what is termed a deep stall. As an airplane enters a deep stall, increasing drag reduces forward speed to well below normal stall speed. The sink rate may increase to many thousands of feet per minute. It must be emphasized that this situation can occur without an excessively nose-high pitch attitude. On some airplanes, it can occur at an apparently normal pitch attitude, and it is this quality that can mislead the pilot because it appears similar to the beginning of a normal stall recovery. It can also occur at a negative pitch attitude, that is, with the nose pointing towards the ground. In such situations, it seems counterintuitive to apply the correct recovery action, which is to push forward on the pitch control to reduce the OA, as this action will also cause the nose to point even further towards the ground. But, that is the right thing to do. Deep stalls may be unrecoverable. Fortunately, they are easily avoided as long as published limitations are observed. On those airplanes susceptible to deep stalls, not all swept or tapered wing airplanes are. Sophisticated stall warning systems such as stick shakers are standard equipment. A stick pusher, as its name implies, acts to automatically reduce the airplane's OA before the airplane reaches a dangerous stall condition, or it may aid in recovering the airplane from a stall if an airplane's natural aerodynamic characteristics do so weakly. Pilots undergoing training in jet airplanes are taught to recover at the first sign of an impending stall instead of going beyond those initial cues and into a full stall. Normally, this 15 to 13. 1. 3. Spanwise flow of boundary layer develops at high CL. 2. 4. Initial flow separation at or near tip. Area of tip stall enlarges. Stall area progresses inboard. Figure 15-16. Swept wing stall characteristics. Is indicated by oral stall warning devices or activation of the airplane stick shaker. Stick shakers normally activate around 107% of the actual stall speed. In response to a stall warning, the proper action is for the pilot to apply a nose-down input until the stall warning stops. Pitch trim may be necessary. Then, the wings are rolled level, followed by adjusting thrust to return to normal flight. The elapsed time will be small between these actions, particularly at low altitude where a significant available thrust exists. It is important to understand that reducing OA eliminates the stall, but applying thrust will allow the descent to be stopped once the wing is flying again. At high altitudes, the stall recovery technique is the same. A pilot will need to reduce the OA by lowering the nose until the stall warning stops. However, after the OA has been reduced to where the wing is again developing efficient lift, the airplane will still likely need to accelerate to a desired airspeed. At high altitudes where the available thrust is significantly less than at lower altitudes, the only way to achieve that acceleration is to pitch the nose downwards and use gravity. As such, several thousand feet or more of altitude loss may be needed to recover completely. The above discussion covers most airplanes. However, the stall recovery procedures for a particular make and model airplane may differ slightly, as recommended by the manufacturer, and are contained in the FAA-approved airplane flight manual for that airplane. Drag devices to the pilot transitioning into jet airplanes. Going faster is seldom a problem. It is getting the airplane to slow down that seems to cause the most difficulty. This is because of the extremely clean aerodynamic design and fast momentum of the jet airplane, and because the jet lacks the propeller drag effects that the pilot has been accustomed to. Additionally, even with the power reduced to flight idle, the jet engine still produces thrust, and deceleration of the jet airplane is a slow process. Jet airplanes have a glide performance that is double that of piston-powered airplanes, and jet pilots often cannot. 15 to 14. OC. Relative wind. OC. VEWIND. RELAT. OC. D. Relative EWN. R. Pre-stall. Initial stall. Deep stall. Pitch altitude. Flight path angle to the horizontal. OC. Angle of attack. Figure 15-17. Deep stall progression. Comply with an ATC request to go down and slow down at the same time. Therefore, jet airplanes are equipped with drag devices, such as spoilers and speed brakes. The primary purpose of spoilers is to spoil lift. The most common type of spoiler consists of one or more rectangular plates that lie flush with the upper surface of each wing. They are installed approximately parallel to the lateral axis of the airplane and are hinged along the leading edges. When deployed, spoilers deflect up against the relative wind, which interferes with the flow of air about the wing. Figure 15-18, this both spoils lift and increases drag. Spoilers are usually installed forward of the flaps but not in front of the ailerons so as not to interfere with roll control. Deploying spoilers results in a substantial sink rate with little decay in airspeed. Some airplanes exhibit a nose-up pitch tendency when the spoilers are deployed, which the pilot must anticipate. When spoilers are deployed on landing, most of the wing's lift is destroyed. This action transfers the airplane's weight to the landing gear so that the wheel brakes are more effective. Another beneficial effect of deploying spoilers on landing is that they create considerable drag, adding to the overall aerodynamic braking. The real value of spoilers on landing, however, is creating the best circumstances for using wheel brakes. Figure 15-18. Spoilers. The primary purpose of speed brakes is to produce drag. Speed brakes are found in many sizes, shapes, and locations on different airplanes, but they all have the same purpose: to assist in rapid deceleration. The speed brake consists of a hydraulically operated board that, when deployed, extends into the airstream. Deploying speed brakes results in a rapid decrease in airspeed. Typically, speed brakes can be deployed at any time during flight in order to help control airspeed, but they are most often used only when a rapid deceleration must be accomplished to slow down to landing gear and flap speeds. There is usually a certain amount of noise and buffeting associated with the use of speed brakes, along with an obvious penalty in fuel consumption. Procedures for the use of spoilers and/or speed brakes in various situations are contained in the FAA-approved AFM for the particular airplane. Thrust reversers. Jet airplanes have high kinetic energy during the landing roll because of weight and speed. This energy is difficult to dissipate because a jet airplane has low drag with the nose wheel on the ground, and the engines continue to produce forward thrust with the power levers at idle. While wheel brakes normally can cope, there is an obvious need for another speed retarding method. This need is satisfied by the drag provided by reverse thrust. A thrust reverser is a device fitted in the engine exhaust system that effectively reverses the flow of the exhaust gases. The flow does not reverse through 180 degrees, however, the final path of the exhaust gases is about 45 degrees from straight ahead. This, together with the losses in the reverse flow paths, results in a net efficiency of about 50%. It produces even less if the engine RPM is less than maximum in reverse. Normally, a jet engine has one of two types of thrust reversers, a target reverser or a cascade reverser. Figure 15-19, target. 15-15. Target or clamshell reverser. Cascade reverser. Figure 15-19. Thrust reversers. Reversers are simple clamshell doors that swivel from the stowed position at the engine tailpipe to block all of the outflow and redirect some component of the thrust forward. Cascade reversers are more complex. They are normally found on turbofan engines and are often designed to reverse only the fan air portion. Blocking doors in the shroud obstructs forward fan thrust and redirects it through cascade vanes for some reverse component. Cascades are generally less effective than target reversers, particularly those that reverse only fan air, because they do not affect the engine core, which continues to produce forward thrust. On most installations, reverse thrust is obtained with the thrust lever at idle by pulling up the reverse lever to a detent. Doing so positions the reversing mechanisms for operation but leaves the engine at idle RPM. Further upward and backward movement of the reverse lever increases engine power. Reverse is cancelled by closing the reverse lever to the idle reverse position, then dropping it fully back to the forward idle position. This last movement operates the reverser back to the forward thrust position. Reverse thrust is much more effective at high airplane speed than at low airplane speeds for two reasons: the net amount of 15 to 16. Reverse thrust increases with speed, and the power produced is higher at higher speeds because of the increased rate of doing work. In other words, the kinetic energy of the airplane is being destroyed at a higher rate at the higher speeds. To get maximum efficiency from reverse thrust, therefore, it should be used as soon as is prudent after touchdown. When considering the proper time to apply reverse thrust after touchdown, the pilot should remember that some airplanes tend to pitch nose up when reverse is selected on landing, and this effect, particularly when combined with the nose-up pitch effect from the spoilers, can cause the airplane to leave the ground again momentarily. On these types, the airplane must be firmly on the ground with the nose wheel down before reverse is selected. Other types of airplanes have no change in pitch, and reverse idle may be selected after the main gear is down and before the nose wheel is down. Specific procedures for reverse thrust operation for a particular airplane/engine combination are contained in the FAA-approved AFM for that airplane. There is a significant difference between reverse pitch on a propeller and reverse thrust on a jet. Idle reverse on a propeller produces about 60% of the reverse thrust available at full power reverse and is therefore very effective at this setting when full reverse is not needed. On a jet engine, however, selecting idle reverse produces very little actual reverse thrust. In a jet airplane, the pilot must not only select reverse as soon as reasonable, but then must open up to full power reverse as soon as possible. Within AFM limitations, full power reverse should be held until the pilot is certain the landing roll is contained within the distance available. Inadvertent deployment of thrust reversers while airborne is a very serious emergency situation. Therefore, thrust reverser systems are designed with this prospect in mind. The systems normally contain several lock systems, one to keep reversers from operating in the air, another to prevent operation with the thrust levers out of the idle detent, and/or an auto stow circuit to command reverser stowage anytime thrust reverser deployment would be inappropriate, such as during takeoff and while airborne. It is essential that pilots understand not only the normal procedures and limitations of thrust reverser use, but also the procedures for coping with uncommanded reverse. Those emergencies demand immediate and accurate response. Pilot sensations in jet flying. There are usually three general sensations that the pilot transitioning into jets will immediately become aware of. These are response differences, increased control sensitivity, and a much increased tempo of flight. In many flight conditions, airspeed changes can occur more slowly than in a propeller airplane. This arises from different effects. At high altitudes, the ability to accelerate lessens due to the reduction in available thrust. Another effect is the long spool-up time required from low throttle settings. Some aircraft can take on the order of 8 to 10 seconds to develop full thrust when starting from an idle condition. Finally, the clean aerodynamic design of a jet can result in smaller than expected decelerations when thrust is reduced to idle. The lack of propeller effect is also responsible for the lower drag increment at the reduced power settings and results in other changes that the pilot will have to become accustomed to. These include the lack of effective slipstream over the lifting surfaces and control surfaces, and lack of propeller torque effect. The aft-mounted engines will cause a different reaction to power application and may result in a slightly nose-down pitching tendency with the application of power. On the other hand, power reduction will not cause pitch changes to the same extent the pilot is used to in a propeller airplane. Although neither of these characteristics are radical enough to cause transitioning pilots much of a problem, they must be compensated for. Power settings required to attain a given performance are almost impossible to memorize in the jets, and the pilot who feels the necessity for having an array of power settings for all occasions will initially feel at a loss. The only way to answer the question of how much power is needed is by saying, whatever is required to get the job done. The primary reason that power settings vary so much is because of the great changes in weight as fuel is consumed during the flight. Therefore, the pilot will have to learn to use power as needed to achieve the desired performance. In time, the pilot will find that the only reference to power instruments will be that required to keep from exceeding limits of maximum power settings or to synchronize RPM. Proper power management is one of the initial problem areas encountered by the pilot transitioning into jet airplanes. Although smooth power applications are still the rule, the pilot will be aware that a greater physical movement of the power levers is required as compared to throttle movement in the piston engines. The pilot will also have to learn to anticipate and lead the power changes more than in the past and must keep in mind that the last 30% of engine RPM represents the majority of the engine thrust, and below that the application of power has very little effect in slowing the 15 to 17 airplane. Power reduction must be made sooner because there is no longer any propeller drag and the pilot should anticipate the need for drag devices. Control sensitivity will differ between various airplanes, but in all cases, the pilot will find that they are more sensitive to any change in control displacement, particularly pitch control, than are the conventional propeller airplanes. Because of the higher speeds flown, the control surfaces are more effective and a variation of just a few degrees in pitch attitude in a jet can result in over twice the rate of altitude change that would be experienced in a slower airplane. The sensitive pitch control in jet airplanes is one of the first flight differences that the pilot will notice. Invariably, the pilot will have a tendency to over-control pitch during initial training flights. The importance of accurate and smooth control cannot be overemphasized, however, and it is one of the first techniques the transitioning pilot must master. The pilot of a swept-wing jet airplane will soon become adjusted to the fact that it is necessary and normal to fly at higher angles of attack. It is not unusual to have about 5 degrees of nose-up pitch on an approach to a landing. During an approach to a stall at constant altitude, the nose-up angle may be as high as 15 degrees to 20 degrees. The higher deck angles, pitch angle relative to the ground, on takeoff, which may be as high as 15 degrees, will also take some getting used to, although this is not the actual lower relative to the airflow over the wing. The greater variation of pitch attitudes flown in a jet airplane are a result of the greater thrust available and the flight characteristics of the low aspect ratio and swept wing. Flight at the higher pitch attitudes requires a greater reliance on the flight instruments for airplane control since there is not much in the way of a useful horizon or other outside reference to be seen. Because of the high rates of climb and descent, high airspeeds, high altitudes and variety of attitudes flown, the jet airplane can only be precisely flown by applying proficient instrument flight techniques. Proficiency in attitude instrument flying, therefore, is essential to successful transition to jet airplane flying. Most jet airplanes are equipped with a thumb-operated pitch trim button on the control wheel which the pilot must become familiar with as soon as possible. The jet airplane will differ regarding pitch tendencies with the lowering of flaps, landing gear, and drag devices. With experience, the jet airplane pilot will learn to anticipate the amount of pitch change required for a particular operation. The usual method of operating the trim button is to apply several small, intermittent applications of trim in the direction desired rather than holding the trim button for longer periods of time which can lead to over-controlling. Jet airplane takeoff and climb. The following information is generic in nature and, since most civilian jet airplanes require a minimum flight crew of 2 pilots, assumes a 2-pilot crew. If any of the following information conflicts with FAA-approved AFM procedures for a particular airplane, the AFM procedures take precedence. Also, if any of the following procedures differ from the FAA-approved procedures developed for use by a specific air operator and/or for use in an FAA-approved training center or pilot school curriculum, the FAA-approved procedures for that operator and/or training center/pilot school take precedence. All FAA-certificated jet airplanes are certificated under Title 14 of the Code of Federal Regulations, 14 CFR, Part 25, which contains the airworthiness standards for transport category airplanes. The FAA-certificated jet airplane is a highly sophisticated machine with proven levels of performance and guaranteed safety margins. The jet airplane's performance and safety margins can only be realized, however, if the airplane is operated in strict compliance with the procedures and limitations contained in the FAA-approved AFM for the particular airplane. Furthermore, in accordance with 14 CFR Part 91, Section 91.213, a turbine-powered airplane may not be operated with inoperable instruments or equipment installed unless an approved minimum equipment list, MEL, exists for that aircraft, and the aircraft is operated under all applicable conditions and limitations contained in the MEL. Minimum Equipment List and Configuration Deviation List. The MEL serves as a reference guide for dispatchers and pilots to determine whether takeoff of an aircraft with inoperative instruments or equipment is authorized under the provisions of applicable regulatory requirements. The operator's MEL must be modeled after the FAA's master MEL for each type of aircraft and must be approved by the administrator before its implementation. The MEL includes a general section, comprised of definitions, general policies, as well as operational procedures for flight crews and maintenance personnel. Each aircraft component addressed in the MEL is listed in an alphabetical index for quick reference. A table of contents further divides the manual in different chapters, each numbered for its corresponding aircraft system designation, i.e., the electrical system, also designated as System Number 24, would be found in Chapter 24 of the MEL. Maintenance may be deferred only on those aircraft systems and components catalogued in the approved MEL. If a malfunctioning or missing item is not specifically listed in the MEL inventory, takeoff is not authorized until the item is 15 to 18. Adequately repaired or replaced. In cases where repairs may temporarily be deferred, operation or dispatch of an aircraft whose systems have been impaired is often subject to limitations or other conditional requirements explicitly articulated in the MEL. Such conditional requirements may be of an operational nature, a mechanical nature, or both. Operational conditions generally include one or more of the following. Limited use of aircraft systems. Downgraded Instrument Flight Rule, IFR, landing minima. Fuel increases due to additional burn, required automatic power unit, APU, usage or potential fuel imbalance situations. Precautionary checks to be performed by the crew prior to departure, or special techniques to be applied while in flight. Weight penalties affecting takeoff, cruise, or landing performance, runway limit, climb limit, usable landing distance reduction, and VRF, takeoff V speeds, and 1/EPR adjustments. Specific flight restrictions involving authorized areas of operation, clearly defined. Geographical regions. Type of operations, international, extended. Operations, ETOPS. Altitude and airspace, reduced vertical separation. Minimums, RVSM. Minimum navigation performance specifications. MNPS. Speed, knots indicated airspeed, KIAS, or Mach. Routing options, extended overwater, reduced navigation capability, high altitude redesign navigation. Environmental conditions, icing, thunderstorms, wind shear, daylight, visual meteorological conditions, VMC, turbulence index, crosswind component. Airport selection, runway surface, length, contamination, and availability of aircraft maintenance, airport rescue and firefighting, ARFF, and ATC services. Listed below are some examples of both operational and mechanical situations that may be encountered. A defective ground proximity warning system, GPWS, would require alternate procedures to be developed by the operator to mitigate the loss of the GPWS and would likely only allow continued operation for 2 days. An inoperative air condition, AC, pack might restrict a Super 80 or a Boeing 737 to a maximum operating altitude of flight level, FL 250, whereas as a Boeing 757 is only restricted to FL 350. An inoperative auxiliary power unit, APU, will not affect the performance or flying characteristics of an aircraft, but it does prompt the operator to verify that ground air and electrical power is available for that particular type of aircraft at the designated destination and alternate airports. A faulty fuel pump in the center tank may lower the maximum zero fuel weight, MCFW, by the amount of center tank fuel, as that fuel would otherwise be trapped and unusable should the remaining fuel pump fail while in flight. At the same time, the unavailability of center tank fuel unmistakably decreases the aircraft range while perhaps excluding it from operating too far offshore. An inoperable generator, IDG, may require the continuous operation of the APU as an alternate source of electrical power throughout the entire flight, and thus more fuel, as it is tasked with assuming the function of the defunct generator. A failure of the heads-up display, HUD, or the autopilot may restrict the airplane to higher approach minima, taking it out of Category 2 or Category 3 authorizations. Mechanical conditions outlined in the MEL may require precautionary pre-flight checks, partial repairs prior to departure, or the isolation of selected elements of the deficient aircraft system, or related interacting systems, as well as the securing of other system components to avoid further degradation of its operation in flight. The MEL may contain either a step-by-step description of required partial maintenance actions or a list of numerical references to the Maintenance Procedures Manual, MPM, where each corrective procedure is explained in detail. When procedures must be performed to ensure the aircraft can be safely operated, they are categorized as either operations procedures or maintenance procedures. The MEL will denote which by indicating an O or an M is appropriate. If operational and mechanical conditions can be met, a placard is issued and an entry made in the aircraft MEL deferral record to authorize the operation for a limited time before more permanent repairs can be accomplished. The placard is affixed by maintenance personnel or the flight crew as appropriate onto the instrument or control mechanism that otherwise governs the operation of the defective device. 15 to 19. In order to use the MEL properly, it is important to clearly understand its purpose and the timing of its applicability. Because it is designed to provide guidance in determining whether a flight can be safely initiated with aircraft equipment that is deficient, inoperative, or missing, the MEL is only relevant while the aircraft is still on the ground awaiting departure or takeoff. It is essentially a dispatching reference tool used in support of all applicable federal aviation regulations. If dispatchers are not required by the operator's certificate, flight crews still need to refer to the MEL before dispatching themselves and ensure that the flight is planned and conducted within the operating limits set forth in the MEL. However, once the aircraft is airborne, any mechanical failure should be addressed using the appropriate checklists and approved AFM, not the MEL. Although nothing could technically keep a pilot from referring to the MEL for background information and documentation to support his decisions, his actions must be based strictly on instructions provided by the AFM, i.e., abnormal or emergency sections. A configuration deviation list, CDL, is used in the same manner as a MEL, but it differs in that it addresses missing external parts of the aircraft rather than failing internal systems and their constituent parts. They typically include elements, such as service doors, power receptacle doors, slat track doors, landing gear doors, APE ram air doors, flaps fairings, nose wheel spray deflectors, position light lens covers, slat segment seals, static dischargers, etc. Each CDL item has a corresponding AFM number that identifies successively the system number, subsystem number, and item number. Flight limitations derived from open CDL items typically involve some kind of weight penalty and/or fuel tax due to increased drag and a net performance decrement, although some environmental restrictions may also be of concern in a few isolated cases. For example, a missing nosewheel spray deflector, Super 80 aircraft, requires dry runways for both takeoff and landing. Each page of the MEL/CDL is divided into 6 columns. From left to right, these columns normally display the following information. Functional description/identification of the inoperative or missing aircraft equipment item. Normal complement of equipment, number installed. Minimum equipment required for departure, number of items. Conditions required for flight/dispatch including maintenance action required, M, by mechanics or other authorized maintenance personnel and operational procedures or restrictions, O, to be observed by the flight crew. These speeds. The following are speeds that affect the jet airplane's takeoff performance. The jet airplane pilot must be thoroughly familiar with each of these speeds and how they are used in the planning of the takeoff. Versus stalling speed or minimum steady flight speed, at which the airplane is controllable. V1, critical engine failure speed or takeoff decision speed. It is the speed at which the pilot is to continue the takeoff in the event of an engine failure or other serious emergency. At speeds less than V1, it is considered safer to stop the aircraft within the accelerate stop distance. It is also the minimum speed in the takeoff, following a failure of the critical engine at VEF, at which the pilot can continue the takeoff and achieve the required height above the takeoff surface within the takeoff distance. VEF speed at which the critical engine is assumed to fail during takeoff. This speed is used during aircraft certification. VR, rotation speed, or speed at which the rotation of the airplane is initiated to takeoff attitude. This speed cannot be less than V1 or less than 1.05 times VMCA, minimum control speed in the air. On a single-engine takeoff, it must also allow for the acceleration to V2 at the 35-foot height at the end of the runway. VLOOF, liftoff speed, or speed at which the airplane first becomes airborne. This is an engineering term used when the airplane is certificated and must meet certain requirements. If it is not listed in the AFM, it is within requirements and does not have to be taken into consideration by the pilot. V2, takeoff safety speed means a referenced airspeed obtained after liftoff at which the required one-engine inoperative climb performance can be achieved. Pre-takeoff procedures: takeoff data, including V1/VR and V2 speeds, takeoff power settings, and required field length should be computed prior to each takeoff and recorded on a takeoff data card. This data is based on airplane weight, runway length available, runway gradient, field temperature, field barometric pressure, wind, icing conditions, and runaway condition. Both pilots should separately compute the takeoff data and cross-check in the cockpit with the takeoff data card. A captain's briefing is an essential part of crew resource management (CRM) procedures and should be accomplished just prior to takeoff. Figure 1520. The captain's briefing is an opportunity to review crew coordination procedures for 15 to 20. Captain's briefing. I will advance the thrust levers. Follow me through on the thrust levers. Monitor all instruments and warning lights on the takeoff roll and call out any discrepancies or malfunctions observed prior to V1, and I will abort the takeoff. Stand by to arm thrust reversers on my command. Give me a visual and oral signal for the following 80 knots, and I will disengage nose wheel steering. V1, and I will move my hand from thrust to yoke. VR, and I will rotate. In the event of engine failure at or after V1, I will continue the takeoff roll to VR, rotate and establish V2 climb speed. I will identify the inoperative engine, and we will both verify. I will accomplish the shutdown, or have you do it on my command. I will expect you to stand by on the appropriate emergency checklist. I will give you a visual and oral signal for gear retraction and for power settings after the takeoff. Our VFR emergency procedure is to. Our IFR emergency procedure is to. Figure 1520. Sample captain's briefing. Takeoff, which is always the most critical portion of a flight. The takeoff and climb out should be accomplished in accordance with a standard takeoff and departure profile developed for the particular make and model airplane. Figure 1521. Takeoff roll. The entire runway length should be available for takeoff, especially if the pre-calculated takeoff performance shows the airplane to be limited by runway length or obstacles. After taxiing into position at the end of the runway, the airplane should be aligned in the center of the runway, allowing equal distance on either side. The brakes should be held while the thrust levers are brought to a power setting specified in the AFM and the engines allowed to stabilize. The engine instruments should be checked for proper operation before the brakes are released or the power increased further. This procedure assures symmetrical thrust during the takeoff roll and aids in prevention of overshooting the desired takeoff thrust setting. The brakes should then be released and, during the start of the takeoff roll, the thrust levers smoothly advance to the pre-computed takeoff power setting. All final takeoff thrust adjustments should be made prior to reaching 60 knots. The final engine power adjustments are normally made by the pilot not flying. Once the thrust levers are set for takeoff. Normal takeoff. Rollout. V2 plus 20 minimum, set climb, accelerate, retract flaps, complete after takeoff climb checklist. Close in turn maintain. Flaps TO and approximately, V2 plus 20 knots, minimum, maximum bank 30 degrees. V2 plus 10 knots minimum. Set takeoff thrust prior. 70 knots check. To 60 knots. V1/VR, rotate smoothly. To 10 degrees nose up. Positive rate of climb, gear up. Figure 1521. Takeoff and departure profile. Straight climb out. V2 plus 10 knots, retract flaps, set climb thrust, complete after takeoff climb checklist. Altitude selected to flap retraction, 400 feet FAA maintain, or obstacle clearance altitude. 15 to 21. Power, they should not be readjusted after 60 knots. Retarding a thrust lever would only be necessary in case an engine exceeds any limitation, such as ITT, fan, or turbine RPM. If sufficient runway length is available, a rolling takeoff may be made without stopping at the end of the runway. Using this procedure, as the airplane rolls onto the runway, the thrust levers should be smoothly advanced to the recommended intermediate power setting and the engines allowed to stabilize, and then proceed as in the static takeoff outline above. Rolling takeoffs can also be made from the end of the runway by advancing the thrust levers from idle as the brakes are released. During the takeoff roll, the pilot flying should concentrate on directional control of the airplane. This is made somewhat easier because there is no torque produced yawing in a jet as there is in a propeller-driven airplane. The airplane must be maintained exactly on centerline with the wings level. This automatically aids the pilot when contending with an engine failure. If a crosswind exists, the wings should be kept level by displacing the control wheel into the crosswind. During the takeoff roll, the primary responsibility of the pilot not flying is to closely monitor the aircraft systems and to call out the proper V-speeds as directed in the captain's briefing. Slight forward pressure should be held on the control column to keep the nose wheel rolling firmly on the runway. If nose wheel steering is being utilized, the pilot flying should monitor the nose wheel steering to about 80 knots, or VMCG for the particular airplane, while the pilot not flying applies the forward pressure. After reaching VMCG, the pilot flying should bring his or her left hand up to the control wheel. The pilot's other hand should be on the thrust levers until at least V1 speed is attained. Although the pilot not flying maintains a check on the engine instruments throughout the takeoff roll, the pilot flying, pilot in command, makes the decision to continue or reject a takeoff for any reason. A decision to reject a takeoff requires immediate retarding of thrust levers. The pilot not flying should call out V1. After passing V1 speed on the takeoff roll, it is no longer mandatory for the pilot flying to keep a hand on the thrust levers. The point for abort has passed, and both hands may be placed on the control wheel. As the airspeed approaches VR, the control column should be moved to a neutral position. As the pre-computed VR speed is attained, the pilot not flying should make the appropriate call-out, and the pilot flying should smoothly rotate the airplane to the appropriate takeoff pitch attitude. Rejected takeoff. Every takeoff could potentially result in a rejected takeoff, RTO, for a variety of reasons: engine failure, fire or smoke. 15 to 22. Unsuspected equipment on the runway, bird strike, blown tires, direct instructions from the governing ATC authority, or recognition of a significant abnormality, split airspeed indications, activation of a warning horn, etc. Ill-advised rejected takeoff decisions by flight crews and improper pilot technique during the execution of a rejected takeoff contribute to a majority of takeoff-related commercial aviation accidents worldwide. Statistically, although only 2% of rejected takeoffs are in this category, high-speed aborts above 120 knots account for the vast majority of RTO overrun accidents. 4 out of 5 rejected takeoffs occur at speeds below 80 knots and generally come to a safe and successful conclusion. The kinetic energy of any aircraft, and thus the deceleration power required to stop it, increases with aircraft weight in the square of the aircraft's speed. Therefore, an increase in weight has a lesser impact on kinetic energy than a proportional increase in ground speed. A 10% increase in takeoff weight produces roughly a 10% increase in kinetic energy, while a 10% increase in speed results in a 21% increase in kinetic energy. Hence, it should be stressed during pilot training that time, delayed decision or reaction, equals higher speed, to the tune of at least 4 knots per second for most jets, and higher speed equals longer stopping distance. A couple of seconds can be the difference between running out of runway and coming to a safe halt. Because weight ceases to be a variable once the doors are closed, the throttles are pushed forward and the airplane is launching down the runway, all focus should be on timely recognition and speed control. The decision to abort takeoff should not be attempted beyond the calculated V1, unless there is reason to suspect that the airplane's ability to fly has been impaired or is threatened to cease shortly after takeoff, for example on-board fire, smoke, or identifiable toxic fumes. If a serious failure or malfunction occurs beyond takeoff decision speed, V1, but the airplane's ability to fly is not in question, takeoff must generally continue. It is paramount to remember that FAA-approved takeoff data for any aircraft is based on aircraft performance demonstrated in ideal conditions, using a clean, dry runway, and maximum braking. Reverse thrust is not used to compute stopping distance. In reality, stopping performance can be further degraded by an array of factors as diversified as runway friction, grooved/non-grooved, mechanical runway contaminants, rubber, oily, residue, debris, natural contaminants, standing water, snow, slush, ice, dust, wind direction and velocity, air density, flaps configuration, bleed air configuration, Underinflated or failing tires. Penalizing MEL or CDL items. Deficient wheel brakes or RTO auto brakes. Inoperative anti-skid. Pilot technique and individual proficiency. Because performance conditions used to determine V1 do not necessarily consider all variables of takeoff performance, operators and aircraft manufacturers generally agree that the term takeoff decision speed is ambiguous at best. By definition, it would suggest that the decision to abort or continue can be made upon reaching the calculated V1, and invariably result in a safe takeoff or RTO maneuver if initiated at that point in time. In fact, taking into account the pilot's response time, the go/no-go decision must be made before V1 so that deceleration can begin no later than V1. If braking has not begun by V1, the decision to continue the takeoff is made by default. Delaying the RTO maneuver by just 1 second beyond V1 increases the speed 4 to 6 knots on average. Knowing that crews require 3 to 7 seconds to identify an impending RTO and execute the maneuver, it stands to reason that a decision should be made prior to V1 in order to ensure a successful outcome of the rejected takeoff. This prompted the FAA to expand on the regulatory definition of V1 and to introduce a couple of new terms through the publication of Advisory Circular, AC 120-62, Takeoff Safety Training Aid. The expanded definition of V1 is as follows. A. V1. The speed selected for each takeoff, based upon approved performance data and specified conditions, which represents 1. The maximum speed by which a rejected takeoff must be initiated to assure that a safe stop can be completed within the remaining runway, or runway and stopway. 2. The minimum speed which assures that a takeoff can be safely completed within the remaining runway, or runway and clearway, after failure of the most critical engine the designated speed, and 3. The single speed which permits a successful stop or continued takeoff when operating at the minimum allowable field length for a particular weight. B. Minimum V1. The minimum permissible V1 speed for the reference conditions from which the takeoff can be safely completed from a given runway, or runway and clearway, after the critical engine had failed at the designated speed. C. Maximum V1. That maximum possible V1 speed for the reference conditions at which a rejected takeoff can be initiated and the airplane stopped within the remaining runway, or runway and stopway. D. Reduced V1. A V1 less than maximum V1 or the normal V1, but more than the minimum V1, selected to reduce the RTO stopping distance required. The main purpose for using a reduced V1 is to properly adjust the RTO stopping distance in light of the degraded stopping capability associated with wet or contaminated runways, while adding approximately 2 seconds of recognition time for the crew. Most aircraft manufacturers recommend that operators identify a low-speed regime, i.e., 80 knots and below, and a high-speed regime, i.e., 100 knots and above, of the takeoff run. In the low-speed regime, pilots should abort takeoff for any malfunction or abnormality, actual or suspected. In the high-speed regime, takeoff should only be rejected because of catastrophic malfunctions or life-threatening situations. Pilots must weigh the threat against the risk of overshooting the runway during a RTO maneuver. Standard operating procedures, SOPs, should be tailored to include a speed call-out during the transition from low-speed to high-speed regime, the timing of which serves to remind pilots of the impending critical window of decision-making, to provide them with a last opportunity to cross-check their instruments, to verify their airspeed, and to confirm that adequate takeoff thrust is set, while at the same time performing a pilot incapacitation check through the challenge and response ritual. Ideally, 2 callouts would enhance a crew's preparedness during takeoff operations. A first call-out at the high end of the low-speed regime would announce the beginning of the transition from low-speed to high-speed, alerting the crew that they have entered a short phase of extreme vigilance where the go/no-go must imminently be decided. A second call-out made at the beginning of the high-speed regime would signify the end of the transition, thus the end of the decision-making. Short of some catastrophic failure, the crew is then committed to continue the takeoff. Proper use of brakes should be emphasized in training, as they have the most stopping power during a rejected takeoff. However, experience has shown that the initial tendency of a flight crew is to use normal after landing braking during a rejected takeoff, delaying the intervention of the 15 to 23 primary deceleration force during a RTO maneuver, when every second counts, could be costly in terms of required stopping distance. Instead of braking after the throttles are retarded and the spoilers are deployed, normal landing, pilots must apply maximum braking immediately while simultaneously retarding the throttles, with spoilers extension and thrust reversers deployment following in short sequence. Differential braking applied to maintain directional control also diminishes the effectiveness of the brakes. And finally, not only does a blown tire eliminate any kind of braking action on that particular tire, but it could also lead to the failure of adjacent tires, and thus further impairing the airplane's ability to stop. In order to better assist flight crews in making a split-second go/no-go decision during a high-speed takeoff run, and subsequently avoid an otherwise unnecessary but risky high-speed RTO, some commercial aircraft manufacturers have gone as far as inhibiting oral or visual malfunction warnings of non-critical equipment beyond a preset speed. The purpose is to prevent an overreaction by the crew and a tendency to select a risky high-speed RTO maneuver over a safer takeoff with a non-critical malfunction. Indeed, the successful outcome of a rejected takeoff, one that concludes without damage or injury, does not necessarily point to the best decision-making by the flight crew. In summary, a rejected takeoff should be perceived as an emergency. RTO safety could be vastly improved by developing SOPs aiming to advance the expanded FAA definitions of takeoff decision speed and their practical application, including the use of progressive callouts to identify transition from low to high speed regime. Promoting situational awareness and better recognition of emergency versus abnormal situations through enhanced CRM training. Encouraging crews to carefully consider variables that may seriously affect or even compromise available aircraft performance data. Expanding practical training in the proper use of brakes, throttles, spoilers, and reverse thrust during RTO demonstrations. Encouraging aircraft manufacturers to eliminate non-critical malfunction warnings during the takeoff roll at preset speeds. Rotation and liftoff in a jet airplane should be considered a maneuver unto itself. It requires planning, precision, and a fine control touch. The objective is to initiate the rotation. To take off pitch attitude exactly at VR so that the airplane accelerates through the loaf and attains V2 speed at 35 feet AGL. Rotation to the proper takeoff attitude too soon may extend the takeoff roll or cause an early liftoff, which results in a lower rate of climb and the predicted flight path will not be followed. A late rotation, on the other hand, results in a longer takeoff roll, exceeding V2 speed, and a takeoff and climb path below the predicted path. Each airplane has its own specific takeoff pitch attitude that remains constant regardless of weight. The takeoff pitch attitude in a jet airplane is normally between 10 degrees and 15 degrees nose up. The rotation to takeoff pitch attitude should be made smoothly but deliberately and at a constant rate. Depending on the particular airplane, the pilot should plan on a rate of pitch attitude increase of approximately 2.5 degrees to 3 degrees per second. In training, it is common for the pilot to overshoot VR and then overshoot V2 because the pilot not flying calls for rotation at or just past VR. The reaction of the pilot flying is to visually verify VR and then rotate. The airplane then leaves the ground at or above V2. The excess airspeed may be of little concern on a normal takeoff, but a delayed rotation can be critical when runway length or obstacle clearance is limited. It should be remembered that on some airplanes, the all-engine takeoff can be more limiting than the engine-out takeoff in terms of obstacle clearance in the initial part of the climb out. This is because of the rapidly increasing airspeed causing the achieved flight path to fall below the engine-out scheduled flight path unless care is taken to fly the correct speeds. The transitioning pilot should remember that rotation at the right speed and rate to the right attitude gets the airplane off the ground at the right speed and within the right distance. Initial climb. Once the proper pitch attitude is attained, it must be maintained. The initial climb after liftoff is done at this constant pitch attitude. Takeoff power is maintained and the airspeed allowed to accelerate. Landing gear retraction should be accomplished after a positive rate of climb has been established and confirmed. Remember that in some airplanes gear retraction may temporarily increase the airplane drag while landing gear doors open. Premature gear retraction may cause the airplane to settle back towards the runway surface. Remember also that because of ground effect, the vertical speed indicator and the altimeter may not show a positive climb until the airplane is 35 to 50 feet above the runway. The climb pitch attitude should continue to be held and the airplane allowed to accelerate to flap retraction speed. However, the flaps should not be retracted until obstruction clearance altitude or 400 feet AGL has been passed. Ground effect and landing gear drag reduction results in rapid 15 to 24 acceleration during this phase of the takeoff and climb. Airspeed, altitude, climb rate, attitude, and heading must be monitored carefully. When the airplane settles down to a steady climb, longitudinal stick forces can be trimmed out. If a turn must be made during this phase of flight, no more than 15 degrees to 20 degrees of bank should be used. Because of spiral instability and, because at this point an accurate trim state on rudder and ailerons has not yet been achieved, the bank angle should be carefully monitored throughout the turn. If a power reduction must be made, pitch attitude should be reduced simultaneously and the airplane monitored carefully so as to preclude entry into an inadvertent descent. When the airplane has attained a steady climb at the appropriate en route climb speed, it can be trimmed about all axes and the autopilot engaged. Jet airplane approach and landing requirements. The FAA landing field length requirements for jet airplanes are specified in 14 CFR Part 25. It defines the minimum field length, and therefore minimum margins, that can be scheduled. The regulation describes the landing profile as the horizontal distance required to land and come to a complete stop on a dry surface runway from a point 50 feet above the runway threshold, through the flare and touchdown, using the maximum stopping capability of the aircraft. The unfactored or certified landing distance is determined during aircraft certification. As such, it may be different from the actual landing distance because certification regulations do not take into account all factors that could potentially affect landing distance. The unfactored landing distance is the baseline landing distance on a dry, level runway at standard temperatures without using thrust reversers, auto brakes, or auto-land systems. In order to meet regulatory requirements, however, a safety margin of 67% is added to the unfactored dry landing distance in the FAA-approved AFM, after applicable adjustments are made for environmental and aircraft conditions, MEL/CDL penalties. This corrected length is then referred to as the factored dry landing distance or the minimum dry landing field length. Figure 1522. For minimum wet landing field length, the factored dry landing distance is increased by an additional 15%. Thus, the minimum dry runway field length is 1.67 times the actual minimum air and ground distance needed, and the wet runway minimum landing field length is 1.92 times the minimum dry air and ground distance needed. Certified landing field length requirements are computed for the stop made with speed brakes deployed and maximum wheel braking. Reverse thrust is not used in establishing the certified landing distances, however, reversers should definitely be used in service. Landing speeds. As in the takeoff planning, there are certain speeds that must be taken into consideration when landing a jet airplane. The speeds are as follows. VSO stall speed in the landing configuration, VRF, 1.3 times the stall speed in the landing configuration. VRF equals 1.3 versus 50 feet. TD. Actual distance 60%. 40%. FAR, dry, runway field length required. 1.67 times actual distance. 15%. FAR, wet, runway field length required. 1.15 times FAR, dry. Or 1.92 times actual distance. Figure 1522. FAR landing field length required. 15 to 25. Approach climb, the speed that guarantees adequate performance in a go-around situation with an inoperative engine. The airplane's weight must be limited so that a twin-engine airplane has a 2.1% climb gradient capability. The approach climb gradient requirements for 3 and 4 engine airplanes are 2.4% and 2.7%, respectively. These criteria are based on an airplane configured with approach flaps, landing gear up, and takeoff thrust available from the operative engines. Landing climb, the speed that guarantees adequate performance in arresting the descent and making a go-around from the final stages of landing with the airplane in the full landing configuration and maximum takeoff power available on all engines. The appropriate speed should be pre-computed prior to every landing and posted where they are visible to both pilots. The VRF speed, or threshold speed, is used as a reference speed throughout the traffic pattern. For example, downwind leg, VRF plus 20 knots, base leg, VRF plus 10 knots. Final approach, VRF plus 5 knots 50 feet over threshold, VRF. The approach and landing sequence in a jet airplane should be accomplished in accordance with an approach and landing profile developed for the particular airplane. Figure 1523. Significant differences. A safe approach in any type of airplane culminates in a particular position, speed, and height over the runway threshold. That final flight condition is the target window at which the entire approach aims. Propeller-powered airplanes are able to approach that target from wider angles, greater speed differentials, and a larger variety of glide path angles. Jet airplanes are not as responsive to power and course corrections, so the final approach must be more stable, more deliberate, and more constant in order to reach the window accurately. The transitioning pilot must understand that, in spite of their impressive performance capabilities, there are 6 ways in which a jet airplane is worse than a piston engine airplane in making an approach and in correcting errors on the approach. The absence of the propeller slipstream in producing immediate extra lift at constant airspeed. There is no such thing as salvaging a misjudged glide path with a sudden burst of immediately available power. Added lift can only be achieved by accelerating the airframe. Not only must the pilot wait for added power, but, even when the engines do respond, added lift is only available when the airframe has responded with speed. The absence of the propeller slipstream in significantly lowering the power on stall speed. There is virtually no difference between power on and power off stall speed. It is not possible in a jet airplane to jam the thrust levers forward to avoid a stall. A beam touchdown point, gear down. A beam runway midpoint, flaps TO approach, VRF plus 20 minimum. 18. 1,500 above field elevation. Turning base, flaps land, reduce power as recommended in the landing profile, start descent, VRF plus 10 minimum. Do not make flat approach. 36. Touchdown, extend speed brake, apply brakes, thrust reverser as required. Complete before landing checklist, maximum bank 30 degrees, clear final approach. Figure 1523. Typical approach and landing profile. 15 to 26. Rollout, reduce speed to VRF, altitude callouts, stabilized in slot. Approach preparations. 1. Reset buck to VRF 2. Review airport characteristics 3. Complete descent and begin before landing checklist. Poor acceleration response in a jet engine from low RPM. This characteristic requires that the approach be flown in a high drag/high power configuration so that sufficient power is available quickly if needed. The increased momentum of the jet airplane making sudden changes in the flight path impossible. Jet airplanes are consistently heavier than comparable-sized propeller airplanes. The jet airplane, therefore, requires more indicated airspeed during the final approach due to a wing design that is optimized for higher speeds. These 2 factors combine to produce higher momentum for the jet airplane. Since force is required to overcome momentum for speed changes or course corrections, the jet is far less responsive than the propeller airplane and requires careful planning and stable conditions throughout the approach. The lack of good speed stability being an inducement to a low speed condition. The drag curve for many jet airplanes is much flatter than for propeller airplanes, so speed changes do not produce nearly as much drag change. Further, jet thrust remains nearly constant with small speed changes. The result is far less speed stability. When the speed does increase or decrease, there is little tendency for the jet airplane to reacquire the original speed. The pilot, therefore, must remain alert to the necessity of making speed adjustments, and then make them aggressively in order to remain on speed. Drag increasing faster than lift, producing a high sink rate at low speeds. Jet airplane wings typically have a large increase in drag in the approach configuration. When a sink rate does develop, the only immediate remedy is to increase pitch attitude, AOA. Because drag increases faster than lift, that pitch change rapidly contributes to an even greater sink rate unless a significant amount of power is aggressively applied. These flying characteristics of jet airplanes make a stabilized approach an absolute necessity. Stabilized approach. The performance charts and the limitations contained in the FAA-approved AFM are predicated on momentum values that result from programmed speeds and weights. Runway length limitations assume an exact 50-foot threshold height at an exact speed of 1.3 times VSO. That window is critical and is a prime reason for the stabilized approach. Performance figures also assume that once through the target threshold window, the airplane touches down in a target touchdown zone approximately 1,000 feet down the runway, after which maximum stopping capability is used. The 5 basic elements to the stabilized approach are listed below. The airplane should be in the landing configuration early in the approach. The landing gear should be down, landing flaps selected, trim set, and fuel balanced. Ensuring that these tasks are completed helps keep the number of variables to a minimum during the final approach. The airplane should be on profile before descending below 1,000 feet. Configuration, trim, speed, and glide path should be at or near the optimum parameters early in the approach to avoid distractions and conflicts as the airplane nears the threshold window. An optimum glide path angle of 2.5 degrees to 3 degrees should be established and maintained. Indicated airspeed should be within 10 knots of the target airspeed. There are strong relationships between trim, speed, and power in most jet airplanes, and it is important to stabilize the speed in order to minimize those other variables. The optimum descent rate should be 500 to 700 fpm. The descent rate should not be allowed to exceed 1000 fpm at any time during the approach. The engine speed should be at an RPM that allows best response when and if a rapid power increase is needed. Every approach should be evaluated at 500 feet. In a typical jet airplane, this is approximately 1 minute from touchdown. If the approach is not stabilized at that height, a go-round should be initiated. Figure 1524. Approach speed on final approach. The airspeed is controlled with power. Any speed diversion from VRF on final approach must be detected immediately and corrected. With experience, the pilot is able to detect the very first tendency of an increasing or decreasing airspeed trend, which normally can be corrected with a small adjustment in thrust. It is imperative the pilot does not allow the airspeed to decrease below the target approach speed or a high sink rate can develop. Remember that with an increasing sink rate, an apparently normal pitch attitude is no guarantee of a normal OA value. If an increasing sink rate is detected, it must be countered by increasing the OA and simultaneously increasing thrust to counter the extra drag. The degree of correction required depends on how much the sink rate needs to be reduced. For small amounts, smooth and gentle, almost anticipatory corrections is sufficient. For large sink rates, drastic corrective measures may be required that, even if successful, would destabilize the approach. 15 to 27. 1000 window. 500 window. Threshold window. Flare. 1000. Stop. Rollout. Touchdown. 50 VRF. Check. For stabilized approach. Stabilized. Approach on. Course on speed 2.5 degrees, 3 degrees glide path. 500 to 700 fpm. Descent. Figure 1524. Stabilized approach. A common error in the performance of approaches in jet airplanes is excess approach speed. Excess approach speed carried through the threshold window and onto the runway increases the minimum stopping distance required by 20 to 30 feet per knot of excess speed for a dry runway and 40 to 50 feet for a wet runway. Worse yet, the excess speed increases the chances of an extended flare, which increases the distance to touchdown by approximately 250 feet for each excess knot in speed. Proper speed control on final approach is of primary importance. The pilot must anticipate the need for speed adjustments so that only small adjustments are required. It is essential that the airplane arrive at the approach threshold window exactly on speed. Glide path control on final approach at a constant airspeed. The glide path angle and rate of descent is controlled with pitch attitude and elevator. The optimum glide path angle is 2.5 degrees to 3 degrees whether or not an electronic glide path reference is being used. On visual approaches, pilots may have a tendency to make flat approaches. A flat approach, however, increases landing distance and should be avoided. For example, an approach angle of 2 degrees instead of the recommended 3 degrees adds 500 feet to landing distance. A more common error is excessive height over the threshold. This could be the result of an unstable approach or a stable but high approach. It also may occur during an instrument approach where the missed approach point is close to or at the runway threshold. Regardless of the cause, excessive height over the threshold most likely results in a touchdown. Beyond the normal aiming point, an extra 50 feet of height over the threshold adds approximately 1,000 feet to the landing distance. It is essential that the airplane arrive at the approach threshold window exactly on altitude, 50 feet above the runway. The flare reduces the approach rate of descent to a more acceptable rate for touchdown. Unlike light airplanes, a jet airplane should be flown onto the runway rather than held off the surface as speed dissipates. A jet airplane is aerodynamically clean even in the landing configuration, and its engines still produce residual thrust at idle RPM. Holding it off during the flare in an attempt to make a smooth landing greatly increases landing distance. A firm landing is normal and desirable. A firm landing does not mean a hard landing, but rather a deliberate or positive landing. For most airports, the airplane passes over the end of the runway with the landing gear 30 to 45 feet above the surface, depending on the landing flap setting and the location of the touchdown zone. It takes 5 to 7 seconds from the time the airplane passes the end of the runway until touchdown. The flare is initiated by increasing the pitch attitude just enough to reduce the sink rate to 100 to 200 fpm when the landing gear is approximately 15 feet above the runway surface. In most jet airplanes, this requires a pitch attitude increase of only 1 degree to 3 degrees. The thrust is smoothly reduced to idle as the flare progresses. The normal speed bleed off during the time between passing the end of the runway and touchdown is 5 knots. Most of the decrease occurs during the flare when thrust is reduced. 15 to 28. If the flare is extended, held off, while an additional speed is bled off, hundreds or even thousands of feet of runway may be used up. Figure 15 to 25. The extended flare also results in additional pitch attitude, which may lead to a tail strike. It is, therefore, essential to fly the airplane onto the runway at the target touchdown point, even if the speed is excessive. A deliberate touchdown should be planned and practiced on every flight. A positive touchdown helps prevent an extended flare. Pilots must learn the flare characteristics of each model of airplane they fly. The visual reference cues observed from each airplane are different because window geometry and visibility are different. The geometric relationship between the pilot's eye and the landing gear is different for each make and model. It is essential that the flare maneuver be initiated at the proper height, not too high and not too low. Beginning the flare too high or reducing the thrust too early may result in the airplane floating beyond the target touchdown point or may include a rapid pitch up as the pilot attempts to prevent a high sink rate touchdown. This can lead to a tail strike. The flare that is initiated too late may result in a hard touchdown. Proper thrust management through the flare is also important. In many jet airplanes, the engines produce a noticeable effect on pitch trim when the thrust setting is changed. A rapid change in the thrust setting requires a quick elevator response. If the thrust levers are moved to idle too quickly during the flare, the pilot must make rapid changes in pitch control. If the thrust levers are moved more slowly, the elevator input can be more easily coordinated. Touchdown and rollout. A proper approach and flare positions the airplane to touchdown in the touchdown target zone, which is usually about 1,000 feet beyond the runway threshold. Once the main wheels have contacted the runway, the pilot must maintain directional control and initiate the stopping process. The touchdown on target. Extended flare. 10 knots deceleration. On ground, maximum braking. 200 feet, dry runway. 500 feet, wet runway. 10 knots deceleration in flare. 2,000 feet, air. Figure 1525. Extended flare. 15 to 29. Stop must be made on the runway that remains in front of the airplane. The runway distance available to stop is longest if a touchdown was on target. The energy to be dissipated is least if there is no excess speed. The stop that begins with a touchdown that is on the numbers is the easiest stop to make for any set of conditions. But more importantly, they spoil much of the lift the wing is creating, thereby causing more of the weight of the airplane to be loaded onto the wheels. The spoilers increase wheel loading by as much as 200% in the landing flap configuration. This increases the tire ground friction force, making the maximum tire braking and cornering forces available. At the point of touchdown, the airplane represents a very large mass that is moving at a relatively high speed. The large total energy must be dissipated by the brakes, the aerodynamic drag, and the thrust reversers. The nose wheel should be flown onto the ground immediately after touchdown because a jet airplane decelerates poorly when held in a nose-high attitude. Placing the nose wheel tires on the ground assists in maintaining directional control. Also, lowering the nose gear decreases the wing OA, decreasing the lift, placing more load onto the tires, thereby increasing tire-to-ground friction. Landing distance charts for jet airplanes assume that the nose wheel is lowered onto the runway within 4 seconds of touchdown. There are only 3 forces available for stopping the airplane: wheel braking, reverse thrust, and aerodynamic braking. Of the 3, the brakes are most effective and therefore the most important stopping force for most landings. When the runway is very slippery, Reverse thrust and drag may be the dominant forces. Both reverse thrust and aerodynamic drag are most effective at high speeds. Neither is affected by runway surface condition. Brakes, on the other hand, are most effective at low speed. The landing rollout distance depends on the touchdown speed, what forces are applied, and when they are applied. The pilot controls the what and when factors, but the maximum braking force may be limited by tire-to-ground friction. The pilot should begin braking as soon after touchdown and wheel spin up as possible, and to smoothly continue the braking until stopped or a safe taxi speed is reached. However, caution should be used if the airplane is not equipped with a functioning anti-skid system. In such a case, heavy braking can cause the wheels to lock and the tires to skid. Both directional control and braking utilize tire-ground friction. They share the maximum friction force the tires can provide. Increasing either subtracts from the other. Understanding tire-ground friction, how runway contamination affects it, and how to use the friction available to maximum advantage is important to a jet pilot. Spoilers should be deployed immediately after touchdown because they are most effective at high speed. Timely deployment of spoilers increases drag by 50 to 60%. 15 to 30. Like spoilers, thrust reversers are most effective at high speeds and should be deployed quickly after touchdown. However, the pilot should not command significant reverse thrust until the nose wheel is on the ground. Otherwise, the reversers might deploy asymmetrically, resulting in an uncontrollable yaw towards the side on which the most reverse thrust is being developed, in which case the pilot needs whatever nose wheel steering is available to maintain directional control. Key points: many LSAs have airframe designs that are conducive to high drag, which, when combined with their low mass, results in low inertia. When attempting a crosswind landing in a high drag LSA, a rapid reduction in airspeed prior to touchdown may result in a loss of rudder and/or aileron control, which may push the aircraft off of the runway heading. This is because as the air slows across the control surfaces, the LSA's controls become ineffective. To avoid loss of control, maintain airspeed during the approach to keep the air moving over the control surfaces until the aircraft is on the ground. LSAs with an open cockpit, easy build characteristics, low cost, and simplicity of operation and maintenance tend to be less aerodynamic and, therefore, incur more drag. The power plant in these aircraft usually provide excess power and exhibit desirable performance. However, when power is reduced, it may be necessary to lower the nose of the aircraft to a fairly low pitch attitude in order to maintain airspeed, especially during landings and engine failure. If the pilot makes a power-off approach to landing, the approach angle will be high and the landing flare will need to be close to the ground with minimum float. This is because the aircraft will lose airspeed quickly in a flare and will not float like a more efficiently designed aircraft. Too low of an airspeed during the landing flare may lead to insufficient energy to arrest the descent, which may result in a hard landing. Maintaining power during the approach will result in a reduced angle of attack and will extend the landing flare, allowing more time to make adjustments to the aircraft during the landing. Always remember that rapid power reductions require an equally rapid reduction in pitch attitude to maintain airspeed. In the event of an engine failure in an LSA, quickly transition to the required nose-down flight attitude in order to maintain airspeed. For example, if the aircraft has a power-off glide angle of 30 degrees below the horizon, position the aircraft to a nose-down 30-degree attitude as quickly as possible. The higher the pitch attitude is when the engine failure occurs, the quicker the aircraft will lose airspeed and the more likely the aircraft is to stall. Should a stall occur, decrease the aircraft's pitch attitude rapidly in order to increase airspeed to allow for a recovery. Stalls that occur at low altitudes are especially dangerous because the closer to the ground the stall occurs, the less time there is to recover. For this reason, when climbing at a low altitude, excessive pitch attitude is discouraged. Chapter Summary: There are many considerations for a pilot when transitioning to jet-powered airplanes. In addition to the information found in this chapter and type-specific information that will be found in an FAA-approved airplane flight manual, a pilot can find basic aerodynamic information for swept-wing jets, considerations for operating at high altitudes, and airplane upset causes and general recovery procedures in the Airplane Upset Recovery Training Aid, Supplement, pages 1 to 14. And all of Section 2 found at www.faa-industry/aviation_visit/airline_operators/training/media/app_upset recovery_book.pdf. 15 to 31. 15 to 32.